Dr. Suzie Sheehy, welcome to Shrink Wrap Radio.
Thanks for having me. It's great to be here.
Well, I'm really excited to have you here. As a matter of fact, we're going to be discussing your 2023 book, The Matter of Everything: How Curiosity, Physics, and Improbable Experiments Change the World. And that's quite a mouthful of a
Yeah,
subtitle, at least. But
it's a long subtitle. Yeah, but I think it accurately describes the story in the book. Yeah,
yeah, it really does. And I understand this is your first book. How did you come to write it?
it is. Yeah. I actually had been chatting to a literary agent for a number of years. Because I did a lot of public speaking, especially when I was working in the UK. And I used to tell all these stories about my field, which is the field of particle accelerators, and the many applications and many different ways that they're used in our society, from cancer treatment to making the chips inside your computer. And this literary agent came and chatted to me one day, and it took about 5 years from that point for me to actually decide I wanted to write a book. But that's kind of how it happened. Yeah, I was lucky enough that someone came to me, and then developing the idea took a little while, I think, to find the right storyline. And every author tells me the same thing, that finding that narrative and that overarching story is really where the work is at. So that took about 5 years.
Yeah, I'm not surprised because you cover so much ground in that book, in this book, I should say. And um, you're an experimental physicist. And I'm a psychologist, of course, and you were asking me just before we got on, well, what's your take going to be on this? Well, mostly we're going to stick to your book, but every now and then I'll come from a psychologist type place. And so the way I'm quite familiar with the idea of an experimental psychologist. And
Mm.
I've interviewed many experimental psychologists on this show. It never occurred to me that there's such a thing as an experimental physicist. This was absolute news to me. But of course, it makes sense, particularly as I dig into your book. But tell us a bit about an experimental physicist, what it is to be one.
Yeah, so I think most of the physicists we come across in popular culture are what I would call a theoretical physicist, right? Someone who is
Yeah.
viewed to be there, like Einstein, there with a piece of paper and a pen, or nowadays a supercomputer, developing theories about the world that we live in. But you really have to think, okay, but who goes out there and verifies whether those theories are true, and who creates who goes out there and experiments with the real world in such a way that we have data around which to build new theories that don't match our background. So the experimental physicist's job really is to go out there and interact with our world, often on tiny microscopic scales that we can't see with our own, eyes, or touch with our hands, and somehow establish truths about our universe that are true. I mean, the wonderful thing about physics is that if you do the experiments in the right way, you can be basically sure that that applies not just in our local area, but whether you're here or in Tanzania, or or on the moon, or in some far reaches of the universe. And being able to develop instruments and equipment and strategies to tease out information about our universe, using that method, is really the art of the experimental physicist. Now, a lot of people think that the theorists do the clever work, and then the experimentalists just go out there and test their clever ideas. In my view, as an experimental physicist, that's not true at all, right? We're really going in there and having to keep our minds open to how the universe works, regardless of the biases that we come in with about whether or not one theory happens to look more compelling. Or often people talk about the beauty of a theoretical idea, or the beauty of mathematics, and we're very biased towards those beautiful ideas. But as an experimenter,
Right.
we have to be open to the idea that the universe might just work in ways that we find theoretically ugly.
Yeah.
um,
We've been so lucky, evidently, because mostly it's turned out to be beautiful.
Exactly. And I guess the tools we have at our disposal as an experimenter as well, we obviously use theory and we use mathematics a lot. I think in physics that's a given, that you have to have that background. But instead of developing new theoretical ideas, we also have to have the background of being able to actually design and make instruments and analyze data. So we might have skill sets that cross from, engineering design of precision components to vacuum systems to detectors to superconductors. So it's quite a wide skill set that you have to bring into the lab to do this.
That's one of the things that really impressed me was your skill set that I think includes things like welding,
Yeah.
electronics, you put together the equipment for these elaborate devices that are going to test out major theories. And I was really impressed by that. And actually, part of my own background is as a young person, I was an amateur radio operator or ham radio operator. I don't know if you've ever run across that. It's a sort of a dying hobby, sort of a dying hobby in some ways. Before the internet, believe me, it was very magical to be able to talk to somebody across town or across the world. And so as a 12, 13, 14-year-old person, that was, for me, was on the frontier. And I took an adult night class on electronics along with some buddies and learned a lot about electronics. And so I worked a lot with vacuum tubes. And it's interesting that your book sort of begins with vacuum tubes and cathode ray tubes and really gets the ball rolling. And you're able to build everything up from there all the way to modern imaging equipment and make it all intelligible. So I'm so impressed by the skill set that you have to have. And, I'm also struck by I wanted to ask you somehow in a way that's not offensive about girls in physics.
Oh yeah, let's get into that. Yeah. This came out as a whole theme of writing this book, and obviously a theme in my own life and experience of being a physicist. So yeah, please ask away.
Well, and then looking at you, you look like you're about 12 years old, which is and maybe you are. I don't know. Yeah.
Maybe Zoom has a good filter on it today. No, significantly older than that. So
I gather not, because you said 5 years you worked on the book, so that's got to be 12 plus 5 is already 17.
At least 17. I can almost drink alcohol in your country. No. So I think one of the things that really came out in writing this book for me, because today we still have this sort of lack of women, especially in the physical sciences and in engineering. And there's really, I'd say in most fields like that, it's roughly 20%. In my own little subfield, designing these big machines, these particle accelerators that we use, it's closer to 10 or 15%. And the further you go up in seniority, the lower that percentage drops, unfortunately. So the number of full professors in my field who are women is pretty low, basically. I'm now associate professor, so soon I'll be there. But we'll get there.
I have no doubt that you'll be there. Yeah.
Oh, that's very kind. So one of the things that happened when I was researching this book, and it happened incidentally, it wasn't planned, was that I was going through these stories back, so I start, as you say, back in about 1896 with these really handcrafted experiments, making these glass vacuum tubes with which to do experiments. And at that time, there's almost no women working in the labs, or at least I thought there was no women at all, other than perhaps Marie Curie, who we've heard about. Yeah. And what surprised me was that stories of women kept coming up in my research process. So there was Harriet Brooks, who was the first graduate student of Ernest Rutherford when he was working in Montreal. And she did some really important work toward understanding radioactive decay and radiation, and understanding an element called thorium and how that decayed. And her experiments were underpinning to our understanding of the concept of radioactive half-life. So that is the decay away in a certain period of time of sort of half of a radioactive element. And she has a really interesting story, because at that time, if you got married, you would have to quit your job. And there were women's colleges, in Montreal at the time, and around the world, there were places that would admit women for higher education. It was pretty rare for them to do physics, but that's what she wanted to do. And she got engaged towards the end of her sort of master's level degree. And she was told that she would have to quit her job and quit physics if she got married by the college that she was working at. And she caused a right fuss, right? Like she really arced up at, like, this is not fair. And they stood by it. And so she actually broke off the engagement and refused to get married in order to continue working in physics. And then
that's
her
devotion
story goes on.
to the
Isn't it?
Yeah.
And it's not like that was easy for her, because she came from a family of like 8 children, and it was not a wealthy family. And, she'd subsisted off scholarships because her family couldn't afford to pay for her to go to university. So she just gave up, financial stability in order to pursue physics. So this passion of women to study this subject has been there all along, and their contributions have been there all along. And I was really pleased to sort of resonate with that experience back through history, not just with someone like Marie Curie, who we've heard of, but with other physicists as well, whom are less well known, including there's a couple of women in about the 1940s, one called Marietta Blau, who's working in Vienna. Another woman, Biba Chowdhury, is working in India at the time. And they're making incredible discoveries, and they're making all their equipment themselves. And I just sort of thought this idea that women, there's still some people who hold the idea that women are somehow not interested in physics, which all the studies prove is not true. They're interested. They just get pushed out culturally of the field as they progress. And I think this was very validating for me to know that interest has always been there, and it has been more the societal factors and the cultural biases that have always prevented women from working in this field. We've obviously come a long way now. Women don't have to quit their jobs when they get married, although in some places that held up until the 1960s and 1970s, believe it or not.
Yeah, I can
but
believe
there are
it.
still pressures. Yeah, there are still pressures, even around that aspect, and around child raising, and around the sharing of household labor. Of course, there's those pressures in someone's life, but even just this sort of bias that we hold that says, think of a physicist, right? And usually a male image comes to our mind.
Sure.
And until we can shift that, I think we're going to continue to have this lack of women. But it was really heartening to me to know that these women have always been there.
Yeah. And in a way, you've kind of tipped your hand for our audience. We haven't described the structure of the book, but the book really consists of a narrative of vignettes of the development of physics, and through a period of mostly around 150 years. Most of it is within that time frame. Some of it goes further back, and then, as you point out, it happens that there are a bunch of women who turn up in this story. But it's an astounding book, because you're taking us through this history of the development of physics, but in the process, we are learning willy-nilly a bunch of really important things about physics, which we may not have majored in or may not have learned that much about on the way. One of the things that really blew my mind, and I'm still wrestling with, is, and it comes up early in the book, is, and I hope I have this right, that matter consists of an up quark, a down quark, and an electron. And that's what matter is throughout the universe, throughout the galaxy. Am I exaggerating, or is that it?
No. I think as far as the matter that we interact with, in terms of the sort of matter particles, or the particles that sort of have mass within that, Yeah, it's literally two types of quarks, the up and down, and those combine together to make the protons and neutrons. And then the electrons, which travel sort of around those in some sense. It's not quite that way quantum mechanically, but sort of travel around those in clouds on the outside of the atom. So if we think about atoms as made up just of protons, neutrons, and electrons, it's just up quarks, down quarks, and electrons, and all the matter that we interact with on our day-to-day basis. Every different material and structure that we experience in our lives is just these three different types of particles. And then if you add light into that equation, which light, matter have sort of some equivalence, but if you sort of add light into that picture, then that's really everything in our everyday experience, from radio waves to getting sunburnt to to the way the internet works. And then as you say, as we look out into the universe, most of what we're interacting with still are those forms of matter that we understand very well, because we can study atoms and things here on Earth, and we can study light here on Earth. And one of the most astonishing things that came through the story of discovery is almost our bias around focusing on that as our definition of matter, because it turns out there's lots of other different types of particles. There's different generations to those quarks that play no role in our atoms. There's different generations to the electron, heavier versions called the muon and the tau, that were discovered over decades, and they play no everyday role in our version of matter either. So I almost got to this point as well, where the book is called The Matter of Everything, and you sort of go, well, that matter, the matter of what we would call everything, is only a small subset of the matter or the particles or the this fundamental constituents of what I would call our whole universe. And not to give the story away, because I think most people can pick this fact up in most science magazines, but you get to today's view of the universe over this incredible journey of 120 years of discovery, and we still look out into the universe and we can see that there are other forms of what I will call matter in inverted commas, such as dark matter, or even the much more mysterious dark energy. And when we look at all of that, we go, oh, we think that all this stuff we've discovered, even if we add up all the atoms and all these muons and all these other things, that might only make up about 4% of the mass energy content of our universe. So there is much, much more out there to discover, and that's the focus of physicists at the moment. And it's quite interesting to me that all of chemistry, all of biology, all of every other science can only focus on this basic form of matter, the electrons and up and down quark.
Yeah.
And yet to a particle physicist, it's like, whoa, hang on, there's like all this other stuff out there. It just doesn't form the everyday atoms that we know and rely on. It's almost it's almost strange that the universe is actually so complex in how in how many different things there are around us every day, and also just the idea that there's particles raining down on us from space all the time, in the form of cosmic rays. There's these tiny ghost-like neutrinos, billions and billions of them are traveling through us every minute. We can't tell at all. They're more common than photons. It's more common than light.
Yeah.
It's you're getting the neutrinos. You're watching neutrinos.
Yeah.
Now, constant neutrino bath your entire life. That's it. And I remember when I was younger and I sort of came across some of these ideas, and it just blew my mind. I sort of thought this world we live in is so much. There's so much to it beyond what we can see and what we can experience with our own senses.
Well, I love also in the introduction you talk about an experience that you had in the Australian outback, of being out under, I guess, sleeping outdoors and sleeping beneath the sky and looking up at the stars. And you had what sounded like a kind of transcendent experience that seemed to magnetize the rest of your life, to give your life this direction that you've taken.
Yeah, it's really, a lot of people who have the experience of stargazing for the first time in a properly dark site, I think, have a similar transformative effect. Because if you lie there long enough, and this is what happened to me, especially in the southern hemisphere, you're looking into the center of the Milky Way galaxy. And so as you lie there and your eyes adjust, the brightness of the star, this band of stars across the center of the sky just appears to get brighter and brighter until you sort of think,
Wow.
how are we not usually cognizant of the fact that we are on a planet sort of 2/3 of the way out on this spiral arm galaxy? And I'm looking toward the center of this galaxy, and we now know, because we've now measured, since I started writing the book, this has been measured, that there is a black hole at the center of our galaxy, and it's now been imaged. Of course, this famous image came out of this sort of fuzzy looking blob with a hole in the center, at the center of our galaxy, which is the supermassive black hole at the center of our galaxy. And I just had this impression as well, if you lay there long enough, that of course that appears to move across the sky. But you go, well, no, hang on. Given this new perspective that I have, and it's kind of like the overview effect, right? That astronauts are said to get when they go up and they see the Earth from a distance. This sort of largening of their perspective. That's how I felt, but lying on the Earth looking in the opposite direction,
Yeah.
where suddenly I can feel that I'm this tiny thing on the Earth, and the Earth is rotating through and moving through this thing we call the universe. And that not only is that, the universe as an entity incredibly complex, but that somehow it has led to me asking questions and wanting to understand it. And it's just almost this closed loop effect where you go, wow, isn't that incredible?
Yeah, it certainly is. And it's hard to hang on to that. Um, but I love the impact that it's had on you and your life, and the way that you're contributing to our knowledge of what's going on. Uh, you know, in coming from psychology, in many people's minds, physics is the gold standard of real science. And so being involved in a quote social science, there was always, people talked about physics envy.
Yeah.
And I think
I've heard that in economics as well, that economics has physics envy.
yeah,
Yeah.
right, physics envy. So so that's certainly one thing that comes up when we think about physics. And another a kind of pet peeve of mine that relates to quantum mechanics and so on is that people write psychological books that are trying to explain things like psychic phenomena and other things that we don't understand, and because there's so much that we don't understand, they kind of fall back on that. That's one version of it, and say, well, we don't know everything, so it could be this and this and this. And then the other thing is that people who are not physics will try to use quantum physics to explain various psychological phenomena. I'm just very distrustful of that.
Yeah. One moment. Sorry.
Yep.
Yeah, that's a bit of a bugbear of mine, or at least at first when I studied physics. And I know a lot of the professors who I studied under, this kind of misuse of the language and concepts of physics to apply to domains where, that are physically much larger than a scale on which the ideas of quantum mechanics are going to make a jot of difference, right? I know a lot of people get annoyed by that. I'm at a point in my career where I'm really curious about the way that we do that. So I'm first of all curious that there are many things that people observe that we can't explain. I think that's fascinating. Withholding some effects which are just almost driven by our cognitive biases, because we like to see things and tell stories in our heads about what it is that we're seeing. But I think one of the things that I became fascinated in, even in writing the book and thinking a little more specifically about the language that we use in physics, is the way that people pick up and use the language and concepts in a metaphorical sense. And I think I'm totally happy for people to use ideas from quantum mechanics, for example, in a metaphorical sense. I actually think that's really valuable. I think, artists and creators and poets can use those ideas to sort of describe things that are otherwise very difficult to describe. And we do that in all sorts of other ways as well. Think about words like pressure, energy, stress. All of these have very technical meanings in physics, and yet we can use them in a broad sense to describe other things that we experience in our life. I think where you get a problem, is where someone is effectively trying to make money off misapplying an idea from quantum mechanics and sort of saying, oh, well, if we just describe this, I don't know, parapsychological phenomenon as quantum, then that explains everything. Yeah. And as a physicist, I'm sort of looking at it going, okay, but you haven't actually explained how that concept is supposed to work. And I can do a calculation on the back of a napkin that shows you that it's not going to work. Or like that the idea is not going to work. At the same time, sometimes these things inspire interesting research areas. So one of the things I read a bit about and would like to read more on is some of the research that's happening in, say, the field that is now called quantum biology. So the idea that some of the effects from quantum mechanics, and really quantum mechanics is a very broad brush, right? Because if you think of an effect like fluorescence or phosphorescence, actually those phenomena only exist because of quantum mechanics, and they can be described quantum mechanically. So, if you go out into nature, you think, well, there are jellyfish that are luminescent. There's natural phosphorescence of things under the ocean, and you sort of think, well, is that a quantum biological phenomenon? ? How do we apply the phrase quantum in a realistic way? And it's a little bit of a gray area, but there are indications of extreme levels of sensitivity in nature. Think about how sensitive the human nose is, for example, or the human ear, and then try and create a sensor that recreates that. And it's really, really difficult. And sometimes our sensitivity to phenomena, is really finely tuned. And that's a pretty incredible thing that I mean, I'm not an expert in this. I'm not a quantum biologist, right? But as I understand it, there are, for example, the tracking of birds in their migration. There have been particular birds that have been found to be incredibly sensitive to the Earth's magnetic field, such that they can navigate by following slight variations in the Earth's magnetic field. Right. And that the only way to describe those very small effects, if you were to write down a theory to describe exactly what's happening in the bird's body or brain or whatever is happening, that you need quantum mechanics to actually describe that. So there are some really interesting areas of research happening where we can take quantum mechanics and apply it to larger scale phenomena and start to understand them. But we are nowhere near the level of trying to understand how that applies to psychology, right? And I very much doubt that psychology or the concepts that we currently have in psychology can just be directly translated and put in this, some kind of superposition concept or some kind of, other than in a metaphorical sense.
Yeah.
Which I think has value. But we do need to delineate between actual science and scientific studies.
Right. And
versus metaphor. Yeah.
Right. And I'm impressed by how broad-minded you're willing to be, how much space you will allow people to do that.
Not every physicist would take that view.
Yeah. You have a
but never say never, right? Never say never. Like right. People, there's many examples in my book of people not being able to believe things even when they had the evidence in front of them. So I guess my own interest in the sort of way that we become biased and the way that we come to think of things as factual has led me to go, well, I'm not going to say that the things these people are saying have scientific basis, but one day someone might do a study that shows that there's some scientific basis to some version of it. And I'm not going to stand here and say 100% that that's not true, because I wouldn't be a scientist otherwise, right? I don't have the evidence to show that it's absolutely not true. So
I'm verging into the realm of things like intuition. I have to say, I'm impressed when I look at the progress of science and so on. What we were taught in experimental psychology in graduate school was that the model of science is that a scientist has a hypothesis which they objectively test And if it doesn't turn out the way that they thought it was supposed to, that they will move on. They abandon that hypothesis and they move on. It seems to me that real people in real life behave quite differently than that. They get this intuition. I think this is how it goes. And they will stick to it over and over and over again for years, trying to come up with a way, with a demonstration that will prove their idea. And in many cases, after years and years of struggle, they finally create the device or the theory that gives it, some substance. So I think that's a very interesting phenomenon.
I agree with you. It's I think there's an important factor there though, and one that people sometimes miss when they go, oh, anyone could come up with a theory that might just turn out to be true if they persist hard enough. One of the things I talk about a little bit in the book is the value of a prepared mind and the ability to ask good questions. And this is why in a field like, I'm sure, like psychology, but also like physics, you go through many years of training and you learn about what has gone before and you recreate the experiments of the past so that you sort of understand the process of developing ideas in physics as a whole. And then I think that's how in physics we talk about developing that physical intuition. And this is also where you get a slight divergence in the training in physics between the more theoretical and the more experimental side. Is some people might just have a real knack for being able to look at equations and sort of go, oh, I think if I do this and this, then it will turn out in this way. Or if I construct it in this way, and years of experience of doing many calculations will sort of give them this ability to frame it in that way. Whereas in the lab, in experimental physics, you might more have a hunch or a learned intuition, I think is probably the best word for it, to say, I don't think that thing I'm seeing on the oscilloscope is real. I think that's noise somehow in my system. And then, questioning everything and going through and proving every single step to yourself so that you understand it deeply enough, you can say, yes, now I've convinced myself that little blip that I'm seeing is real. And now I have to consider what physics might produce that blip in my system. I think the other thing that particle physics has done, because it relies so heavily on like really difficult statistical methods, right? Where it's pulling out, needle in a haystack would be easy compared to a Higgs boson discovery, right? You're looking for tiny effects in large amounts of data. And so they've developed not just the statistical methods to tell them whether or not that's a real effect, but also systems to unbias themselves from what they believe should be in the data. So they have a process called blinding the data in the big particle physics experiments now, where they collect all the data from the experiments and keep it hidden even to themselves. And they develop all their analysis tools so that, the tools that are designed to pull out these little peaks or these little blips. They run that either on simulated, like fake data, or they run it on some very small subset of the real data. And so when they go through this process at the end of unblinding, then they can be sure that they haven't just designed that analysis in order to pull out something which is fake. That said, in the stories, I tell a number of stories of how some of those blips in earlier days looked like they were real, and then when you collected more data, they went away again. And that's why they've developed these incredibly sophisticated ways of trying not to fool themselves into thinking that something is true or real about the universe, when in fact the data, it's just noise in the data. And so we also have then this incredibly high standard of evidence that we call this 5 sigma standard of evidence. And if you apply that 5 sigma, I can't remember the exact percentage, but it's like there's a 1 in 99.9999999 chance that the phenomenon is not explained by your theory, right? Or that your hypothesis is sort of wrong. I'm not explaining that well, but there's a very high standard of evidence.
In psychology, we talk about standard deviations. So I think the 5 sigma that you're talking about would be 5 standard deviations. out.
It's roughly
Yeah,
equivalent to that, yeah.
yeah.
And my understanding is if you applied that standard of evidence to almost any other field of science, all the results would disappear. And so we're lucky in physics in that way that we can design our experiments and repeat the experiments again and again and again to gather enough data to be really sure of these very, very tiny phenomenon. And that's one of the reasons why we get these big experiments and these, interesting tiny effects. But in our field, we've learned that those tiny effects are sometimes where the interesting science is.
I'm always intrigued by the seeming paradox of the fact that I'm saying the fact, it may not be a fact,
Mm-hmm.
my notion that mathematics is a rational process based on reasoning, human reasoning, outside of physical evidence, and yet it becomes the gold standard for evaluating physical phenomena. Seems to me there's a paradox there.
That's a really wise question, I have to say.
Thank you.
That's a big question. So one of the things that I think is most amazing to most of my theoretical physics colleagues is the idea that the universe can be described by mathematics at all, right?
Yeah.
Why is it that these number structures and things that we've developed over centuries, millennia, are actually able to describe accurately the workings of the universe? That's in the realm of philosophy. That's really, I'm fascinated by that as well, the fact that our universe can be described mathematically. I'm sure there are fields in which so far we haven't been able to do the same thing. So for example, a lot of biology, a lot of even more complex areas of chemistry, thus far we haven't been able to fully describe them using mathematics, or at least certainly not in the that sort of very predictive mathematical sense. And that's where you get new areas of mathematics emerging that are more statistical in nature, or that can describe more chaotic or complex processes. And then, again, you sort of regain this ability to describe systems in terms of mathematics. And to me, it is one of the most wonderful things about the way we work in science, is that this stuff can be described by mathematics. Why that's the case, it seems to be almost sheer coincidence that is the case in most of the time. And yet the only way in our society that we can make predictions and understand things to the level of detail where we can use it for our own benefit, for the benefit of society, to build things or make things, or make our lives easier or better or longer, is to use this process. I think it's much more satisfying anyway, to a physicist anyway, to be able to write down an equation to describe something than it is to say, okay, well, I did this experiment, I took this data set, I have no idea how to interpret it fundamentally, but here's the plot, here's the data.
Yeah.
And I think that the task and the interaction between experimentalists and theoretical scientists in, I would say, any field, is this ability to work together to go, okay, well, how do we interpret this data? What does this mean in the context of our models or our theories? And how do we put that together to actually gain insight about the actual world around us? And I think this is also why I've ended up in a very open-minded sense about how we use words in physics, how we use concepts of physics, because I can see all the way from this spectrum of like the very detailed mathematical models being exact and trying to predict, like we can predict the evolution of our solar system a long way out in the future, and we're going to get it almost exactly correct because we understand that so well. And yet, you probably can't predict what your slightly chaotic friend is going to do tomorrow. Right. So I think, so it's like, okay, we have to hold space for these the things which we can describe to this level of detail, which are very useful to us, and have been the foundation of things like modern medicine, the way we travel, the way we work, the way we interact with each other. All these things are actually underpinned by these fundamental ideas that science has given us. But we also can't forget that on the other end of the spectrum, we're humans, and that we usually can't, even though it is probably the goal. I don't define the goals of psychology to a psychologist, but we can't almost be as predictable as that. We're never going to be. And I think somewhere in the middle, there's space for creativity and acceptance, and just going, yeah, you know what, we're flawed human beings, and yet look at what we can do and what we can be and what we can create, and the ways in which we can thrive together. So I know a lot of physicists who are sort of very much of the opinion that if you can't pin it down with mathematics, and if it doesn't have this fundamental underpinning, and basically if it's not physics, then it's not valuable. That's completely wrong in my view, because it completely negates the human element of who we are and how we live, and even who we are when we do science, and the questions that we ask. And why is it that you decided in your career to ask questions about psychology, and I decided to ask questions about fundamental particle physics?
Yeah, I subscribe to the idea of appropriate levels of to come in at appropriate levels for research. So in other words, on the one hand, everything is based on atoms and subparticles and light and so on. But to understand human behavior, even though it's based on all of that stuff, it's not the best way to approach it. It's
right.
It's going way down too far on the scale, right? And so that's why social sciences and biological sciences and other things, they also find important truths, but it's a whole different level of an analysis.
Exactly, on a different scale.
Yeah. But I want to jump over a whole bunch of your book and go to your work, which is very fascinating. And so tell us about what you say you design. Well, you say it in your own words.
Yeah.
What you're creating.
So when people ask me what I do nowadays, I say I design particle accelerators. And most of the time now I'm designing those for medical applications or for other societal applications. So let me rewind on that a bit. So in the book, we go through this journey of people developing the first machines that could take subatomic particles and make them go faster, effectively, for useful means. And in the book, originally, this is trying to split the atom for the first time, which happened in around 1932, using one of the first particle accelerators in Cambridge in the UK. And since then, this technology of taking, sort of ripping apart atoms to take protons or to take electrons, and then pushing them up to high energy, controlling them, and then using them to do something, being able to design a system that does that is sort of the art of particle accelerators, or accelerator physics, which is my sort of subfield. And almost immediately on the discovery of these different phenomena in radiation, so X-rays were discovered in 1896, and within a year they were being used to take images on battlefields and in hospitals to try and help find shrapnel and things in people's bodies to try and save lives. So people tend to take the discoveries of physics and the tools of physics and apply them in areas which may not have been obvious to the discoverer. And this is also true of particle accelerators. So as we've been able to make machines which are better controlled, higher energy, cheaper, more reliable, ones that could produce different beams or beams of greater intensity or smaller size, lots and lots of uses have come up for them. So now there's about 50,000 particle accelerators in the world. Most people are pretty surprised by that.
Yeah, because I think of a particle accelerator as something like CERN, or there's miles and miles, a big circle of thing that,
Right, right. And if there
and
were 50,000 of those, we'd know about it, right?
yeah,
But that's just
right.
the big ones, right? Like they're just the ones used by physicists. But the ones used by physicists are like a fraction of a percent of all the ones on Earth. And so actually what's happened is that as these technologies have developed, they've found many other uses in society. So one of the main ones is using small linear accelerators. So that's, sort of a small meter long accelerator that's sort of in a straight line, to accelerate electrons and then turn those into X-rays just by hitting a metal target with the electrons. And then using those, shaping the X-rays to actually target tumors and cancers and areas inside people's bodies. And
Yeah.
this is the process called radiotherapy. And in your country, or my two countries, the UK or Australia, about half of all cancer patients are treated using radiotherapy. And yet most people have no idea that inside that is a little particle accelerator that benefited from developments in radar in World War II, benefited from the particle physics developments that happened at Stanford that later led to discovering the quarks, the fundamental constituents of protons and neutrons. And there's this wonderful story about doing that. But nowadays, we're able to actually develop technologies more specifically for those applications so that they can sorry, I just had a message on this side. Sorry, we can develop those technologies more specifically for the application so that we can make them smaller, we can make them more reliable. We can target tumors and cancers a lot better than we could. And we develop those now in collaboration with oncologists and medical physicists and people who work with patients. And this is something that when I finished my undergraduate degree and I went to do my PhD, and I sort of found out about this in a way, I found that the tools of fundamental physics were being used already to treat cancer in hospitals. And I sort of thought, oh, wow, that's amazing. That brings together my sort of big picture fundamental physics, long-term view of discovery with, this sort of desire I had also to do something that had an impact more immediately in the world. And so eventually, I've worked in a number of different research areas, but eventually I came back to starting a new lab when I moved back to Australia a few years ago to focus on these smaller types of accelerators, some of which are used in hospitals in just like small meter long ones, some of which are much more substantial. So they're sort of almost not quite football field size, but a little bit larger. And they're used for more precise forms of cancer treatment using protons and heavier ions, so particle therapy, as we call it, which has the ability to more precisely target the areas that we need and give a higher radiation dose to those areas while not destroying the healthy tissue. Along the way, I've also found that one of the interesting things is as our technologies have become more advanced, we also have to consider the equity of access to those technologies. And it wasn't until 2016 when a new collaboration formed and I went to some meetings at CERN that I even discovered, I sort of knew in the back of my mind that, of course, like we have these devices in our hospitals and they save lives every day. But if you go to, say, Zimbabwe, they might not. And I got involved in this collaboration a few years ago now that's trying to understand from both a technology but also a global health perspective, how to improve access to this kind of high-tech cancer treatment technology in low and middle income countries. Because by 2035, 70% of all cancer cases around the world are going to be in low and middle income countries, not in high income countries. So it's a growing problem. There's a massive shortfall of these devices.
Yeah.
And even if we built one a week, it would take 50 years to even make up the current shortfall. So it's really an issue. And as people are doing amazing work towards solving sort of some of the more transmissible diseases, things like malaria, and trying to intervene on those, and populations get healthier and populations get older, the incidence of cancer actually increases. So we have to start addressing this issue now, and the technologies that we have just break down more frequently. They're not designed for those environments. They have to go in hospitals that can be very difficult for people to get to if they live in remote areas. And so one of the things I'm quite passionate about now is trying to understand where from a technology perspective, we can actually make a difference in trying to make those machines more robust or more accessible or smaller. And so that's been a real pleasure to sort of put my values together with the technology.
What wonderful. And I was struck by, I'm of an age where I've been subjected to many different imaging devices in hospitals. And you point out that some of those imaging devices, like for PET scans and other kinds of scanning that are in local hospitals, that they use atomic processes, right?
So CT scans are sort of the culmination of using X-rays. MRI scans, they absolutely use what's called nuclear magnetic resonance, which I won't go into, but it's a wobble on a nucleus, all driven by high-tech stuff like superconducting magnets that wouldn't have been possible without these large-scale physics projects. There's a story in the book about the Tevatron in the US and how that led to the industrialization of superconducting wire that now we rely on in things like MRI scanners, and then even PET scanners, as you said. That one is positron emission tomography. They literally use antimatter annihilating with normal matter in order to image inside the body.
I've been in one of those.
Did you have to take like a sweet liquid, or did they feed you a
Oh sweet... they gave me. I think they injected me with with something that they could, atomically scan. That would show up.
So that's usually they use fluorodeoxyglucose or FDG, and the fluoro bit is a fluorine 18. Which is a radioactive element, very low level of radioactivity. I want to assure everyone out there that there's no sort of danger of the radiation that is involved in this process. But that's actually a positron emitter, so it emits particles which are the antimatter version of the electron. And so wherever that accumulates in the body, and it tends to go to areas that have a high metabolic region. So whenever there's sort of an injury in the body, all the blood rushes there, and it's a highly metabolized area. So it tends to gather there. And then these positrons come out, they find the nearest electron inside you, they annihilate and send out 2 photons in opposite directions. And then there's a ring of detectors around you that catch those 2 photons, and that's how it builds up an image. It's just an amazing.
So you're telling me I've been bombarded with antimatter?
Yeah. For good.
Incredible to think of. Incredible. So
this stuff is there all the time, and you go into a hospital and some doctor says, "Oh, we're going to send you for this scan," and we sort of look at the company name on the scan and we think, "Oh, this company invented that. They're clever," and you don't attribute it to fundamental research. But actually, these things take decades and decades, starting from the very fundamental idea all the way through to, the ability of a company to sell a product that can then be used in a reliable way in something like a hospital or an industry. And I think we sometimes lose sight or maybe glamorize even the entrepreneur or the company or that end of things, while we forget that they wouldn't have any ideas to work with or to develop into products if it wasn't for the people working at that more fundamental end. So we do need to value that research, I think.
Definitely. So who should read your book?
Oh, everyone.
I agree with that. It would be good for everyone to read.
I think if you're curious, if you have, especially if you're someone who likes to put stories around sometimes difficult ideas, if that helps you, and the human stories as well, that's something that we really focused on in developing the narrative of the book. And also, if you just like putting together these seemingly disparate ideas, like the connection between the development of microwaves and the discovery of quarks, and all these, and the first IPO in Silicon Valley, I will note as well, is related to this story. If you like putting these disparate ideas together, then I think the book is for you.
Yeah, I agree. I highly recommend it. Well, Dr. Suzie Sheehy, I want to thank you for being my guest, most lively and fascinating guest today on Shrink Wrap Radio.
Thank you so much, and thanks for the wonderful questions.